In this video, we are diving into the heart of wave mechanics. We will unravel the mathematics behind the progressive waves, explore wave phases, and measure wave intensity. Just like skilled surfer, we will navigate through the equations, defining their journey and understanding the power these waves carry. Real-world examples will guide us. So, let's surf through progressive wave essentials and set you on a path to triumph, especially for NEET. Ready? Let's make wave in under a minute. Progressive wave is like a ripple in water. When you drop a tiny droplet, picture it like a dance on the water surface. When the water is calm and you disturb it, little waves form. These waves move energy from one water part to another, somewhat like passing a message. The water particles goes up and down, but they don't move sideways. Imagine a duck on a water. Even when the waves pass through, the duck stays in its place. The water at the surface does a little circular dance, creating the ripples we see. Let's simplify it. We can use a sophisticated equation to describe the movement of particles as it responds to passage of wave. In a progressive wave, each particle undergoes a consistent back and forth motion. They all move at the same speed and execute identical dance steps. But there is a twist. They might be at different points in their dance routine. Take a look at the animation illustrated the birth of two waves. Observe how each one has its own distinct frequency but same wavelength. They resemble two dancers moving in unison along with the positive x-axis, each following its unique rhythm in the lively wave dance. Did you notice that for the same wavelength, high-frequency sound travel faster than the low-frequency sound? So, we can say wave velocity depends upon the frequency of wave. The equation for the wave velocity is given by V is equal to n lambda. Here, n is a frequency and lambda is the wavelength. General equation for progressive wave along positive x-axis is given by y x comma t equals to a sine kx minus omega t plus y. Here k is equal to 2 pi upon lambda is the wave number and omega is equal to 2 pi by t is called as angular frequency. Now let's see each and every term appearing in the equation. Y x comma t is a vertical displacement of a point on the wave at position x and time t. That is, it is up and down motion of a particle along y-axis. Capital A, that is the amplitude indicating the maximum height of the wave. Sine function responsible for the up and down pattern of the wave. X, position of a particle along the horizontal axis. Capital T is the periodic time of wave. Small t, time, representing when we are observing the wave. Y, phase constant, determining the starting point of the wave. Now, we will obtain a general equation in terms of wavelength and periodic time by substituting k and omega. We get y x comma t is equal to a sine of 2 pi upon lambda into x minus 2 pi upon capital T into small t. Further simplification, by taking 2 pi upon lambda common, we get y x comma t is equal to a sine into square bracket 2 pi upon lambda into round bracket x minus lambda t divided by capital T round bracket close square bracket close. Now we will further obtain wave equation in terms of wave velocity. Velocity of a wave is given by the equation lambda upon t. Therefore, replacing lambda upon t in the previous equation, we get y x comma t is equal to a sine 2 pi upon lambda into bracket x minus vt bracket close. Now, we will obtain a velocity of wave equation in terms of k and omega. we know that V is equal to lambda upon T. Therefore, V is equal to lambda upon 2 pi divided by T upon 2 pi. Therefore, we get V is equal to lambda upon 2 pi into 2 pi upon T. Since 2 pi upon lambda is k and 2 pi upon t is omega, we get the equation for the velocity of wave v is equal to omega upon k. These equations provide a comprehensive understanding of wave displacement and velocity, allowing us to explore the intricate dance of progressive waves through space and time. Now, we will use a little bit of calculus to find out the velocity of a particle by taking the derivative of displacement y with respect to time. We get dy by dt is equal to v equal to minus a omega cos of kx minus omega t. When cos of kx minus omega t is equal to 1, then we get maximum velocity v max is equal to a omega. That is, maximum velocity is at the equilibrium position of the particle and acceleration is 0. Now we will obtain a formula for acceleration of a particle by taking the derivative of velocity with respect to time. We get dv by dt is equal to a equal to plus a omega square sine of kx minus omega t. Here note that derivative of cos of theta is minus sine theta. Therefore, we get the positive sign in acceleration. If sine of kx minus omega t is equal to 1, then the maximum acceleration a max is equal to a omega square. Maximum acceleration is achieved by a particle when it displaces to its highest point of amplitude, at which velocity becomes 0. Now we will go through the relationship between phase difference and path difference. Delta phi, that is the phase difference, is equal to k into delta x. Here, delta x is path difference. Let's go through a characteristics of progressive wave. Vibrating particles. Particles move around their mean position, creating a disturbance that travels through the medium. Uniform amplitude. All particles vibrate with the same amplitude, indicating a constant range of motion. Successive replication. Successive particles imitate the motion of their predecessors, but at a slightly delayed time. Phase changes. The phase of each particle shifts from 0 to 2 pi during its vibration. No permanent rest. No particle stays permanently at the rest. They reach the extreme position at different times. Wave types. Transverse waves have crest and troughs, while longitudinal waves have compression and rarefaction. Energy transfer. Energy transfers across the medium in the direction of wave propagation. Equal maximum velocity. All particles reaches the same maximum velocity as they pass through the mean position. Uniform displacement, velocity, and acceleration. Particles separated by a distance m lambda exhibit the same displacement, velocity, and acceleration, where m is an integer. In simple terms, progressive waves involve particles moving uniformly, sharing the same vibrational characteristics, and transferring energy in a specific direction through the medium. The behavior of each particle is synchronized, creating a dynamic and consistent wave pattern. Now, let us delve into the captivating world of sound quality, where frequency, pitch, and wavelength play a symphony of roles. Quality of a sound. The quality of a sound is intricately determined by three key elements: frequency, pitch, and wavelength. These elements collectively shape the way we perceive and experience sound waves. Let's explore the fascinating world of frequency and pitch. Frequency, an objective and measurable quantity, represents the number of oscillations in a sound wave per second. Now, let's visualize this concept through four distinct animations. High frequency. Imagine a sound wave with a high frequency, resulting in rapid oscillations. Visualize how this translates to a high pitch. Low frequency. Transition to another scenario with a sound wave characterized by a low frequency, featuring slower oscillations. Observe how this corresponds to low pitch. Noise. Explore the concept of noise, where multiple frequencies combine in a complex manner. Witness how this amalgamation can lead to an intricate and less defined pitch. Harsh sound. Lastly, envision a scenario of harsh sound where a specific frequency or combination creates jarring effect. Witness how certain frequencies contributes to the perception of harshness. In contrast to frequencies objectively, pitch is subjective and perceived by our ears. Hearing frequencies generally mean higher pitches, while lower frequencies results in lower pitches. What makes this intriguing is that pitch perception goes beyond just its frequency and can be influenced by various factors. Within the classroom, a unique symphony of sounds unfolds. Picture this: girls often engaging with higher-pitched voice, appealing complex qualities, contributes to a vibrant sonic landscape distinct from that of the boys. Why the difference? Well, it boils down to the natural frequencies. Woman's voice naturally resonates at high frequencies, while the man's voice carry lower frequencies. Delving into the intricate realm of acoustics, high frequencies, like those found in the girl's voice, possess a remarkable ability. They can gracefully navigate through the background noise. Envision a bustling street or a crowded room. The focused directionality of a high-frequency voice allows girls to communicate more efficiently in such environments. Now, here is a fascinating tidbit for the boys. Your voice, with their lower frequencies, encounter a distinctive challenge. Low-frequency sounds tend to disperse and get absorbed by obstacles. In the midst of lively environment, your words might not travel as efficiently as that of girls. So, here is a simple tip in a noisy places. Opt for a concise conversation, or when necessary, amplify your amplitude. Consider it a friendly suggestion to avoid unnecessary shouting and attracting unintended attention. When a wave encounters an unyielding boundary, magic happens. It reflects. Picture a wave happily cruising along only to meet a solid wall. Instead of giving up, it elegantly bounces back. The reflective wave is like a mirror image, performing a graceful opposite dance to the original. Up becomes down and down becomes up, a wave waltz. This interplay creates a unique pattern known as reflection. Wave does not disappear when faced with an immovable force. They elegantly turns around, leaving their marks with a special flip. This dance between the waves and the boundary is the reflection symphony in the world of physics. A brief but beautiful performance in the great concert of the universe. Reflection of waves from free end. Imagine a dance of waves, a string tied to ring gliding on a smooth rod. Our free end. When a wave's pulse hits, the ring shoots up, stretching the string and makes the mirrored pulse. Together, they form a strong waves picking at the end. Surprisingly, this reflection happens smoothly without a change in phase. In big picture of wave reflection, this scenario is special. Boundaries between the material act differently. Solid boundaries flip the phase, while open ones reflect without a phase change. In the world of waves, it is like a symphony, a subtle dance between the freedom and reflection. Let's explore these waves with the liveliness of a free end on a vertical rod. The loudness of sound depends on intensity and ear sensitivity. Intensity defined as the amount of energy crossing per unit area per unit time perpendicular to the wave's propagation, measured in watts per meter square. Intensity depends on amplitude of the source, surface area of a source, density of the medium, frequency of the source, and the distance of the observer from the source. By combining this, we can find out a formula as I is proportional to S into rho into bracket AN upon R bracket close raised to 2. Before we delve into solving some intriguing problems, I would like to encourage you to visit our website www.gnit.com for concise notes and numerous practice questions. Solving the questions right after studying a lesson enhance memory and retention of the material. The interesting thing is that it is an entirely free website, not even registration is required. In this question, you are presented with 4 wave equations, and your task is to pinpoint the one that does not represent a wave moving in positive x-axis. Each option has its own arrangement of amplitude, sign functions, and the variable k and omega. The equation y is equal to minus a sine into bracket kx minus omega t, option C, does not represent a wave moving in positive x-axis because of the negative sign in front of amplitude. The negative sign indicates that the wave is inverted compared to the standard waveform y is equal to a sine kx minus omega t. Thus, represents a wave moving along negative x-axis. This is a NEET 2023 question. From the graph, we get amplitude A is equal to 1 meter, periodic time t is 8 seconds, and initial phase is 0 radians. Asked to find the acceleration at time 2 seconds. The equation for the wave moving in positive x-axis is given by y is equal to a sine of kx minus omega t. If we take the derivative of the standard equation, we get velocity. U is equal to minus a omega cos of kx minus omega t. By taking the derivative of velocity u with respect to time, we will get a is equal to plus a omega square sine of kx minus omega t. Note, derivative of cos theta is equal to minus sine theta. Therefore, negative signs cancelled out and a become positive. By substituting the value of k and omega, we get the equation a is equal to a omega square sine of 2 pi upon lambda into x minus 2 pi upon t into small t. Given values of time t is equal to 2 seconds, lambda is equal to 4 meter, x is equal to 2 meters, and from graph a is equal to 1 meter, t is equal to 8 seconds, we get a is equal to a omega square sine of 2 pi upon 4 into 2 minus 2 pi upon 8 into 2. On simplifying, we get a is equal to omega square sine of pi minus pi by 2, which is equal to omega square sine of pi by 2. Sine of pi by 2 is 1. Therefore, we get a is equal to omega square. As omega is equal to 2 pi upon capital T, we get a is equal to 2 pi upon T. A is equal to into bracket 2 pi upon T bracket close raised to 2. Substituting the value of T and solving it, we get a is equal to pi square upon 16 meters per second square. Option B is correct. In this question, wave equation is y is equal to a sine omega t plus kx, and asked to find after what fraction of the time period will the velocity of a point be equal to half of its maximum velocity. By taking the derivative of wave equation with respect to time, we get the equation for the velocity as v is equal to a omega cos of omega t plus kx. For maximum value of velocity, cos of omega t plus kx must be equal to 1. So, maximum velocity occurs at integer multiples of the time period. Therefore, omega t1 plus kx is equal to n pi. For half of maximum velocity, we will substitute the value of v as v max upon 2, and we get the equation as v max upon 2 is equal to a omega cos of omega t plus kx. But we know that a omega is v max. Therefore, we get the equation as half is equal to cos of omega t plus kx. To get the value of cos as half, we should have omega t2 plus kx is equal to n times of pi by 3. Now we got two equations. Initial equation is omega t1 plus kx is equal to n pi for maximum velocity, and another equation omega t2 plus kx is equal to n times of pi by 3 for the velocity half of the maximum velocity. By subtracting half velocity phase from the maximum velocity phase, we get omega t1 plus kx minus omega t2 minus kx equals to n into bracket pi minus pi by 3 bracket close. Now we will take the value of n is equal to 1. Therefore we get omega t1 minus omega t2 is equal to 2 pi upon 3. Taking out omega common, we get omega into bracket t1 minus t2 bracket close is equal to 2 pi by 3. T1 minus T2 can be considered as delta T, and omega is 2 pi upon capital T. We get 2 pi by capital T into delta T is equal to 2 pi by 3. Therefore, delta T is equal to T by 3. Therefore, the fraction of the time period after which the velocity of a point will be equal to half of its maximum velocity is T by 3. In this equation, the transverse wave is described by the equation y is equal to a sine of nt minus x upon lambda. Asked to find a maximum particle velocity equal to 4 times of the wave velocity. Maximum particle speed Vmax is equal to a omega. Omega is 2 pi upon time. Therefore, we get Vmax is equal to a into bracket 2 pi into n. Wave velocity is given as lambda into n. Therefore, a into bracket 2 pi n bracket close is equal to 4 lambda n. Therefore, lambda is equal to pi a by 2. Option B is correct. In this question, the sound has a frequency of 500 Hz and velocity is 350 meters per second. Asked to find out the distance between the two particles, now we will first of all calculate the value of lambda, because if phase difference is 2 pi, then path difference is lambda. Now, V is equal to n into lambda, therefore 350 is equal to 500 into lambda. On simplifying it, we get lambda is equal to 0.7 meters. Now, if the phase difference is 2 pi, the distance between the two particles, that is the path difference, is 0.7. Then, for pi by 3 or 60 degrees, what the phase difference will be? By using the simple mathematics, we can find that difference in the particle is 0.1166 meters or 116.6 centimeter approximated to 120 centimeter. Option B is correct. In this question, the amplitude of sound is doubled and the frequency reduced to 1/4. Asked to calculate the intensity of a sound at the same point. I is directly proportional to S, that is a surface, into rho, that is density, into bracket A n upon R bracket close raised to 2. A is amplitude, n is frequency, and R is the distance of a point from the source. Now, replacing A by 2A and replacing the frequency n by n by 4, we get I dash is proportional to 1 by 4 SP into bracket A n upon R bracket square. Therefore, if we take the ratio of I dash to I, we get I dash upon I is equal to 1 by 4. Intensity decreases by 4. Option C is correct. In the next video, we will delve into the fascinating topics of superposition of waves, standing waves, and harmonics. This is Avinash signing off. Thank you for joining us on this educational voyage. Before you go, remember to hit the like button and subscribe to our channel for more insightful content. Until next time, happy learning.